Today, we're going to continue looking at reference angles. Once again, we want to put angles in on the Cartesian plane because we want our angles to break out of the confines of the triangles that we had them in before. We need to look at sine, cosine, and tangent of some non-acute angles. Last time, we defined how we're going to do this. We set things up on the coordinates where the positive x-axis was 0 degrees, and then counterclockwise was the positive direction. So through each quadrant, we go for, we have quadrant 1 will cover angles between 0 degrees and 90 degrees. Quadrant 2 will cover angles between 90 degrees and 180 degrees. Quadrant 3 will cover angles between 180 and 270. And quadrant 4 will be angles from 270 to 360. Past 360, we could just go around again from 360 to 720, and then we can just keep going around. So really, we should focus on 0 to 360, because anything beyond 360 is going to be on this same circle. Similarly, if we have negative angles are also going to be in the same on the same circle. So negative 0 degrees and negative 90 degrees will be down here in quadrant 4. From negative 90 to negative 180 will be in quadrant 3. From negative 180 to negative 270 will be in quadrant 2. And from negative 270 to negative 360 will be in quadrant 1. So if we can understand what's going on between 0 and 360, all the other values, all the other angles will correspond to an angle between 0 and 360. So that's where we really have to understand things. Then it's just going to be a matter of adding or subtracting full circles to get into this range from 0 to 360. So that's what we really want to understand. Last time, we defined what standard position was, where the initial side would be on the positive x-axis, counterclockwise would be the positive direction, and then the terminal side will terminate in one of these quadrants or on the x or y axis. Reference angles were always going to be measured. Reference angles were always going to be measured from the terminal side of the angle, to the nearest part of the x-axis. So here in quadrant 1, whatever the angle is, that's going to be the reference angle. In quadrant 2, we're going to go from the terminal side of the angle to the nearest part of the x-axis. So we're going to keep going until we get to the negative side of the x-axis. That's where we'll put our reference angle. In quadrant 3, we'll have a terminal side, and the nearest part of the x-axis will be the negative x-axis again, and we'll have to go back to the negative x-axis. And in quadrant 4, the nearest x-axis, the nearest part of the x-axis will be the positive x-axis. So we'll just keep on going and see how much further we need to go to finish out the circle. So here I've labeled 45-degree reference angles in each of the 4 quadrants. So each of these 45-degree reference angles, or each of these 45-degree angles, is going to be a reference angle for a theta. So I'm going to label them as theta sub r for reference angle. So a subscript of r is going to indicate a reference angle. We just want to figure out between 0 and 360 what angles have a 45-degree reference angle in each quadrant. In the first quadrant, the reference angle is just the angle itself. So a 45-degree angle will have a 45-degree reference angle. In the first quadrant, theta is equal to theta r. In the second quadrant, we have a 45-degree angle between the negative x-axis and the terminal side of theta. Remember, theta is measured starting at the positive x-axis and going counterclockwise. So that's where we would label the angle theta. It's 45 more degrees to get to the positive, the negative x-axis. And so if we just subtract 45 from the 180, that'll tell us what the angle theta is in quadrant 2 with the 45-degree reference angle. So in this case, we'll take 180 and subtract the reference angle. And so that 180 minus 45 is 135. So if we have a 135-degree angle, that's going to terminate in quadrant 2, and it's 45 degrees away from the negative x-axis, which is at 180 degrees. In quadrant 3, if I draw a 45-degree reference angle, if we start at the positive x-axis, we go 180 degrees to the negative x-axis, and then 45 more degrees to get to theta, that has a 45-degree reference angle in quadrant 3. So we go 180 degrees and then 45 more degrees. So 180 plus 45 is going to be a 225-degree angle. So a 225-degree angle is a 45-degree reference angle in quadrant 3. And then we keep going. Going all the way around would be 360. So if I go back 45 degrees, I can take 360 and subtract 45, and we'll be at 315 degrees. So 315 degrees is a 45-degree reference angle in quadrant 4. 315 is 45-degree reference angle in quadrant 4. $225 is a 45-degree reference angle in quadrant 3. $135 is a 45-degree reference angle in quadrant 2. And 45 is a 45-degree reference angle in quadrant 1. So these reference angles, these 45-degree reference angles, not only apply to 45, 135, 225, and 315, but also any angle that terminates, or any angle that is coterminal with 45, 135, 225, and 315. So if I have 45-degree, an angle that terminates, that's coterminal with 45 degrees, I could also go around one full circle at 360 and add another 45. So also theta is equal to 360 plus 45. So 405 degrees also has a 45-degree reference angle in quadrant 1. Because if we subtract off a full circle from 405 degrees, I end up with 45 degrees. So the 405 is coterminal with 45. If I go around again and take 405 and add another full circle, that will be at 765. 765 is also coterminal with 45. And that will also be the same 45-degree reference angle in quadrant 1. So if we're looking at an angle 765 degrees, we know that that's past 2 full circles. we subtract the 2 full circles off, we can see that that's coterminal with 45 degrees. And so then we can just figure out what the reference angle is. We can also go backwards. So 315 degrees, we can also read as negative 45 degrees. So if we're looking at negative 45 degrees, if I add a full circle, negative 45 degrees is coterminal with 315 degrees. Now we know that 315 has a 45-degree reference angle. So the numbers that we want to know are between 0 and 360. Those are the ones that we want to focus on. And we want to identify 45, 135, 225, and 315 as angles with a 45-degree reference angle. The ones we want to identify, 45, 135, 225, and 315. Don't got to memorize those numbers. We just want to remember them. And we want to associate those 4 angles with 45-degree reference angles in the first, second, third, and fourth quadrants. So we know that with this 45-degree angle, we know that from an isosceles right triangle, that sine of 45 and cosine of 45 are both square root of 2 over 2. So we know that if we build our isosceles right triangle, we know that sine of 45 is 1 over the square root of 2, which we were writing as root 2 over 2. And we know that cosine of 45 is adjacent over hypotenuse, which is also 1 over the square root of 2, which we were writing as root 2 over 2. Oh, and tangent of 45 is opposite over adjacent, which we'll just write as 1. So there's got to be some kind of connection between the the root 2 over 2 and these angles with a 45-degree reference angle. The other thing that we want to remember, I'm just going to pick sine, or I'm going to pick cosine. I always pick sine. I'm going to go with cosine this semester. The other thing that we want to remember is are the values of cosine going from 0 up to 90. So if you would recall, we listed values of cosine when we said cosine of 0 was 1. Cosine of 30 is root 3 over 2. Cosine of 45 is root 2 over 2. Cosine of 60 is root 1 over 2, better known as a half. And then cosine of 90 was equal to 1. What we want to do is, cosine of 90 is 0. See, I normally do sine first. I switch it up on the fly, and you should never do that. Just go with what your plan is. Don't let yourself call audibles, especially when you're recording a class. So Michael, I always do sine. And so like my little trigonometry quarterback was like, oh, Omaha, Omaha. And then all of a sudden, Michael, I'm going to go with cosine. And then I start messing things up. I don't know if this lack of focus is a more coffee problem or a less coffee problem, but I know what solution I'm going to apply. So I think I got this sorted out. Cosine of 0 is 1. Cosine of 30 is root 3 over 2. That's about 0.8770. Root 2 over 2 is 0.7071. 1/2 is 0.5, and then 0 is 0. So cosine starts off at 1, and then the first quadrant drops down to 0. We can associate these with the x-coordinates if we go around a unit circle. So the coordinates at this point are going to be 1, 0. The coordinates corresponding to theta equals 0 are 1, 0. And the coordinates corresponding to theta equal 90 are 0, 1. So what we're going to track with cosine through this first quadrant is the x-coordinate. So the cosine theta is the x-coordinate on the unit circle. So the association that we want to make is that cosine of theta is going to get we're going to get from the x-coordinate on the unit circle. This tells us that cosine of theta is positive whenever x is positive. Cosine theta is positive when x is positive. X is positive in the first and the fourth quadrant. X is positive in the first and fourth quadrants. So cosine theta is positive in the first and fourth quadrants. So the values we're going to get from the reference angle, the sign we're going to get from the quadrant. And this is how we're going to put things together. Here's how we're going to remember what's positive where. Cosine theta is going to come from the x-coordinate on the unit circle. So that, oops, there we go. Cosine theta is positive when x is positive. X is positive in quadrant 1 and quadrant 4, so cosine theta is positive in quadrant 1 and quadrant 4. So putting this together, back on our unit circle with these 45-degree reference angles, we know that the cosine of 45 is equal to root 2 over 2. That's the value. And we know that cosine is positive in the first and fourth quadrant. So the cosine of 45 is going to be positive root 2 over 2. Because 45 is in the first quadrant, cosine is positive in the first quadrant. When we go down to 315, 315 has a 45-degree reference angle, and it's in quadrant 4. So if we want to know the cosine of 315, we'll get the value from the reference angle, cosine of 315. The value comes from the reference angle of 45. Cosine of 45 is root 2 over 2. And cosine is positive in quadrant 4. So cosine of 315, positive root 2 over 2. So that means if cosine is positive when x is positive, that means cosine is negative when x is negative. That means cosine is going to be negative in quadrant 2 and quadrant 3. So when we want to know the cosine of 135, we get root 2 over 2 from the reference angle, and we get negative from the quadrant. So the cosine of 135 is going to be negative root 2 over 2. Negative because 135 terminates in quadrant 2 where cosine is negative. Root 2 over 2 because cosine of the 45-degree reference angle is root 2 over 2. Similarly, in quadrant 3, we'll have the cosine of 225 will be negative root 2 over 2. Negative because because theta is 225 terminates in quadrant 3, and cosine of theta is negative in quadrant 3 because x is negative in quadrant 3. And root 2 over 2 because the cosine of 45-degree reference angle is root 2 over 2. Value from the reference angle and the trig function, sine from the quadrant and the trig function. Any questions? So if cosine is going to be associated with x, so cosine theta is positive when x is positive, you can probably guess what we're going to do with sine. So let's list our values of sine that we know and our 3 reference angles. We know that sine of 0 degrees is 0. The sine of 30 degrees is a half. Sine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. And sine of 90 is 1. So if we go from 0 to 90 degrees, and we're going to start off at 0, and then at 30, we're at the sine of 30 is a half, sine of 45 is root 2 over 2, sine of 60 is root 3 over 2, sine of 90 is 1. Going from 0 to 1, we're tracking the y values. So sine theta is going to be the y coordinate on the unit circle. Sine theta is the y coordinate on the unit circle. This is going to tell us where sine is positive and negative. So sine theta is positive when y is positive. Y is positive in quadrant 1 and quadrant 2. So sine theta is positive in quadrant 1 and quadrant 2. Cosine is positive when x is positive. Sine is positive when y is positive. So we'll do the same thing going around the circle. So if I want the sine of 45, 135, 225, and 315, those are all 45 have, well, those all have 45-degree reference angles. So sine of 45, we get the value √2/2 from the trig function and the reference angle, and we get the sine positive from the trig function and the quadrant. Going around to quadrant 2, if I want the sine of 135, (135) has a 45-degree reference angle. Sine of 45 is √2/2. We get the value from the trig function and the reference angle. And sine is positive in quadrant 2. So sine of 135 is positive √2/2. To get the sine of 225, we get the value from the trig function and the reference angle. So sine of 45 is √2/2. 225 is in quadrant 3, and sine is negative in quadrant 3. So the sine of 225 is negative √2/2. And then at 315, the sine of 315 has a 45-degree reference angle in quadrant 4. So the sine of 45 is √2/2. That's where we get the value. And sine is negative when y is negative, and in quadrant 4, y is negative. So sine of 315 is negative √2/2. Going around with this XY coordinate thing going on the unit circle, we start off at 0 degrees, we're at the point 1, 0. At 90 degrees, we're at the point 0, 1. So at 180 degrees, we're over here at the point -1, 0. And at 270, we're at the point 0, -1. So these points tell us some stuff. We're associating the x with the cosine and y with sine. So at 180, we can say that the cosine of 180 degrees is -1, because cosine is the x, and sine of 180 is 0, because sine is the y. We can keep going around to 270, we're at the point 0, -1 on this unit circle. So cosine of 270 is 0, the x coordinate, and sine of 270 is -1, the y coordinate. Then back up to theta equals 0. Cosine of 0 is 1, sine of 0 is 0. Cosine is the x, sine is the y. Now we have all these coordinates in the middle at these 45-degree angles. Cosine is the x, sine is the y. So the coordinates of this point where 45 degrees hits the unit circle will be root 2 over 2, root 2 over 2. The x and the y coordinates are both positive because the cosine and the sine are both positive in quadrant 1. If I look at the coordinates where 135 hits the unit circle, they're both going to have a value of root 2 over 2, but the x coordinate is negative. Makes sense. Cosine is negative in the second quadrant. Cosine is the x, so the coordinates of this point will be negative root 2 over 2 and positive root 2 over 2. Negative on the x, positive on the y. Negative cosine, positive sine in quadrant 2. Going around to where 225 hits the unit circle, we have a negative x coordinate and a negative y coordinate, and the values are negative root 2 over 2, negative root 2 over 2. And finally, since I'm super out of space, where 315 hits the unit circle, we'll have a positive x, so positive root 2 over 2, and a negative root 2 over 2 for the coordinates there. Because x is positive, y is negative. Because in quadrant 4, cosine is positive and sine is negative. So we're going through these same values in this same progression. We got the 0, 1/2, root 2 over 2, root 3 over 2, 1. And then going, continuing the y coordinates back around the circle, we're off a y coordinate of 1. We go from 1, root 3 over 2, root 2 over 2, 1/2, 0. Then we're going to be in quadrant 3, and sine is going to be negative because y is negative in quadrant 3. We'll be at 0, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. And then from 270 to 360, we'll go from negative 1 to negative root 3 over 2 to negative root 2 over 2 to negative 1/2 to 0. So going around, we're just going to go up and down these values. This only seems like it's a lot to remember because it's a lot to remember. And you have to remember all of it all the time in perfect detail. However, we have a big advantage in remembering all this information. There's a lot of different patterns. So that means there's a lot of different ways to make connections with all these things that you have to remember. Look at all the different patterns. And that way you'll be able to find out which one works best for you. Let's look at some more reference angles. I'll use my circle drawing thing. I don't know if I've demonstrated my cool circle thing, but you twist it and you can make smaller circles. So for those of you Stargate fans, I have like a miniature chop of eye here. It also comes with this thing so you can locate where the center of your circle should go. And this is one of my favorite math toys. I'm going to put the center of the circle right here. And I just have to draw my circle. So cool. Good for drawing a nice circle. What's terrible is that I draw this nice circle, I located the center, and then instead of using a ruler, I just like use the grid and I draw these wobbly axes. And so you're like looking at this really nice circle, and then I mess it up with these little wobbly axes. Part of it is that this particular style of pen doesn't get along well with rulers. So in case you're curious about drawing tools, this is an Iris drawing compass, the company's maker's cabinet. So this is not a sponsored video, but this is a really, really cool circle drawing toy. Works much better than like a compass. Compasses always slide out. All right. So this is all still the stuff we had before. So I want to mark the quadrant angles where theta is 0 and 360 degrees. Up here, we have theta equals 90 degrees. Over here at this end, we have theta is equal to 180 degrees. Down here, theta is equal to 270. And I also, since I'm associating sine and cosine with y and x, set it backwards, I also want to label these points. So here's the point 1, 0. (90 degrees is at the point 0, 1. 180 on the unit circle is -1, 0. 270 on the unit circle is 0, -1. And now we're going to put in 30 and 60 degree reference angles. Point. So if you're playing along at home, the way I'm figuring out where these angles are going to be is I'm going to look for halfway. Because I know one of my values is going to be 1/2. I know that sine of 30 is equal to 1/2. And so I'm going to look for where the y coordinate is equal to 1/2. And that's where 30 degrees is going to intersect the unit circle. I happen to be lucky that the maximum size of this gives me 1, 2, 3, 4 squares on my grid. But let's draw our 30-degree reference angles. So here's 30 degrees in quadrant 1. This thing. So here are 30 degrees in quadrant 1 and 30 degrees in quadrant 3. And then we also have 30 degrees in quadrant 2 and 30 degrees in quadrant 4. And this angle, I struggle a lot with drawing. So sorry for kind of going Batman angle on you here. But I didn't draw this ahead of time. See, if you had a professional teacher, this would have been all ready to go as the second slide. But unfortunately for y'all, you're stuck with me. So here, we have 30-degree reference angles in quadrant 1, 30 degrees in quadrant 4, 30 degrees in quadrant 2, and 30 degrees in quadrant 3. And we want to figure out what angles these correspond to. Once again, we just care about the ones from between 0 and 360. So a 30-degree reference angle in quadrant 1 will just be 30 degrees. In quadrant 4, if we go negative 30 degrees, we can subtract 30 from 360, and we'll be at a 330-degree angle. Going over to the quadrants 2 and 4, if we go 180, we'll be at the negative y-axis. And then if we go backwards 30 degrees, we'll do 180 minus 30. So 150 degrees corresponds to a 30-degree reference angle in quadrant 2. And a 30-degree reference angle in quadrant 4 will be 180 plus 30, so 210 degrees. We could write down formulas, 4 different formulas for how to calculate a reference angle based on an angle, and then turn those around to figure out what the angle is based on the reference angle. I would rather not use a formula and just remember how we figure out the reference angle. So we can just get about remembering rather than try to remember formulas. I think too often in math, we just try to default to formulas when we don't really need to. So. Incidentally, I see the indeed there, and it has a certain sound in my, I read that in Tilt's voice. So I can't do that voice, but that's how I heard that. So. We also want to look at the 60 degrees, 60-degree reference angles, because they come from the same triangle. So we always put those together. So once again, I could locate the 60s by looking at where x is equal to 1/2. And then that's how I can get my 60-degree angles. So here are four 60-degree reference angles. And we can do the same thing. We want to go around and identify the 4 numbers that we will associate with a 60-degree reference angle in each of the 4 quadrants. That will be 60 degrees in quadrant 1 because it's always just matching. In quadrant 2, we'll take 180 minus 60, and so that'll be a 120-degree angle. In quadrant 3 will be 60 degrees after 180. So that'll be a 240-degree angle. And in quadrant 4, it'll be 60 degrees before 360, so a 300-degree angle. So for our 30, we have these 4 angles: 30, 150, 210, 330. I want to picture those in this spot right here, in those 4 spots. Then we want to picture the 60, 120, 240, and 300. We want to associate those with 60-degree reference angles. Those are our 4 60-degree reference angles. Then we just want to make sure that we know sine and cosine of all these values. And we want to associate them with points going around this unit circle. X coordinate for cosine, Y coordinate for sine. I'm going to list cosine and sine of each of these as coordinates going around the unit circle so we could see the progression. We know that cosine of 30 is root 3 over 2. So the x coordinate of where the 30 degrees hits the unit circle is root 3 over 2. And the y coordinate is the sine, and sine of 30 is 1/2. In the middle is where we'd have root 2 over 2 times root 2 over 2 and root 2 over 2. So we go from, cosine is going to go from 1 to root 3 over 2 to root 2 over 2 to 1/2. And root 3 over 2. We see the cosine counting down from 1 to 0 in the first quadrant, while sine counts up from 0 to 1 in the first quadrant. It gets real crowded if I throw the 45-degree angle in the middle, but it fits with the pattern. Cosine goes 1, 0.877, 0.707, 0.50. Then continuing on around the circle, at 120, we're going to have the 60-degree reference angle. But in the second quadrant, cosine is negative and sine is positive because x is negative and y is positive. So the coordinates of this point, we're going to have the same values, but the x will be negative here. So negative 1/2, positive root 3 over 2. We'll have the same values at 150 that we saw at 30 because we have the same reference angle. But in the second quadrant, cosine is negative and sine is positive. So the coordinates at 150 will be a positive 1/2 and a negative root 3 over 2. Then we continue on to 210. We'll have the same values because we still have the same reference angle. So x will be a root 3 over 2, and y will also be, x will be the negative, x will be root 3 over 2, and y will be 1/2. And they'll both be negative because in the third quadrant, sine and cosine are both negative, which makes sense because x is negative and y is negative. So these coordinates are both going to be negative. At 240, we have a 60-degree reference angle. So we're still going to have 1/2 and a root 3 over 2, but they're both going to be negative because now we're in quadrant 3. At 270, we're at 0,1. At 300, we have a 60-degree reference angle. So we'll still have a 1/2 and a root 3 over 2. But x is positive in the fourth quadrant and y is negative in the fourth quadrant. So we'll have, I hit spacebar after my parentheses. 1/2 is positive and the negative root 3 over 2 is negative. X is positive and y is negative.
So for the 210, that should be, x should be negative 1/2. Is that what it is, or is it just blurred together there?
That is a negative. That should be a negative 1/2 at 240 down here. So that one goes with the negative 1/2. Negative root 3 over 2 goes with the 240. And then finally for 330, we're going to have a root 3 over 2 and a 1/2. The root 3 over 2 will be positive because x is positive. But the 1/2 is negative because we're in the fourth quadrant. This only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. However, you have a lot of patterns going on around here, and looking for the patterns and looking for all the symmetry and knowing where things come from will help you remember all these values. The goal is for me to say, what is the sine of 120? And you to immediately come up with root 3 over 2. This is your new times tables for trigonometry. Just like if I ask what's 7 times 8, you just say 56, right? Yeah, 56. You say that immediately. You don't have to think about it. You just know it. It might be because you memorize your times tables, which sounds like an awful thing to do, but that might have been what you had to do when you were a kid. So I don't fault you for doing it that way. Or it might just be that you remember because you've done so much multiplication in your mathematical history that you just remember that now. This is probably not a thing anymore, but I remember phone numbers that I used to dial all the time, like all my friends' phone numbers from when I was 12, because you had to dial the whole number. I didn't sit down and memorize those numbers. I just dialed them so much, I just started remembering them. So I didn't actively memorize the numbers. I just looked at it and dialed it so many times, I didn't need to look at it anymore. I just started remembering. So that's what you do with these values. You just draw yourself a unit circle and just start filling in the coordinates all the way around the circle for 30, 45, 60, and 90. All the way around 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360. And then you just list the coordinates going all the way around. Do that a couple of times and you won't have to memorize the values. You'll just remember what they are. I suppose we could be pedantic about this thing and say, well, by doing that, that's how you're memorizing them. But you do that a couple times and you'll start seeing the patterns that will help you remember. Cosine is positive when x is positive, sine is positive when y is positive. The values are 1, root 3 over 2, root 2 over 2, 1/2, 0, 1/2, root 2 over 2, root 3 over 2, 1, root 3 over 2, root 2 over 2, 1/2, 0, and they just go around. Any questions? Comments? Snide remark? All right. So, like I said, it's a lot to remember, but there's a lot of patterns. Look for patterns and look for symmetry, because the patterns and the symmetry are going to help you remember. You start by doing things in a particular order, and you build up that pattern before you start having the random access. So you want to build it up to the point where you have random access to all these different values. Now, we're not building this random access because later on in your future job as an engineer working on the human mission to Mars or whatever, because we're going to build a colony up there. I doubt that that's going to hinge on whether or not you remember that sine of 30 is 1/2 and that 150-degree 150 degrees has a 30-degree reference angle in the second quadrant. And so sine of 150 is also positive 1/2. That's not why we're doing this. We're doing this is because it's good training. And we're going to eventually take the theta, and instead of having theta just go around the unit circle continually, we're going to stretch theta along a horizontal axis. And we're going to start building functions that go up and down like this. And that's going to represent theta going, or the y coordinate going around the circle, starting off at 0, 1/2, √2/2, √3/2, 1, √3/2, √2/2, 1/2, 0, -1/2, -√2/2, -√3/2, -1, and so on. It's going to go up and down. Because there are a lot of functions that have that kind of behavior, where the function just goes up and down and up and down and up and down. Any questions? How's everybody okay? It's like before you could do all the math stuff where you start learning how to multiply two-digit numbers. You got to learn your times table for all the one-digit numbers. You got to learn 7 times 8 is 56, so you can use that when it comes up in 72 times 18, because there's a 7 times 8 in there. It's actually a 70 times 8, but to do that problem, 70, I can't remember what I said, 72 times 18, to do that problem, at some point, you're going to need to know 7 times 8 is 56. Any questions? Comments? Snide remarks?
So I guess I got a question. So when you've got these memorized, like your times tables, can you give an example of how you would use that with different angles? How it's going to simplify problems with some angle that's not 30, 60, or 45?
So it's going to help in the sense that when we calculate, when we look at a problem and it's got, let's say, a 30, like in the problem that we had a 36 degree angle, and we need to know the sine of 36. We know that sine of 36 is going to be between sine of 30 and sine of 45, so it'll give us a good basis to work with. So sine of 30 is 1/2, sine of 45 is √2/2. So since 36 is between 30 and 45, we're looking for something between 0.5 and 0.7. And so that gives us an idea about where the sine of 36 should be. That doesn't help. These values are not going to be translate directly into calculating the sine of 36. Because if it's anything but a multiple of 30, 45, 60, or 90, we're going to use other means. We're going to grab our slide rule and calculate the sine, cosine, and tangent of those angles. But when we start drawing graphs, we don't want to have to resort to the slide rule to get those values, to get an idea about the shape of the graphs. So I don't have like a super strong justification, because you could just be like, oh, what if I just look it up all the time? And we could just look it up all the time. You could be like, okay, what's the sine of 150 on our calculator? And it's going to come out 0.5. And we recognize it. And if it's like, oh, make the fraction. What if you need the fraction? You just have to remember that 0.5 is a 1/2. And then if we need the cosine of 210, the calculator is going to tell us it's negative 0.8660. But our experience is going to tell us that that's just negative √3/2. So it's just kind of filling in. It gives us a good place to start when we start looking at trig functions of other angles.
Okay, and a good sanity check, so you know if you're approximately way off, you made some kind of huge error and you're getting something totally different from what you expect.
Right. So if, for example, you say 150 times the answer is supposed to be 88, and you accidentally hit cosine instead of sine, and you put down 121. I don't know what kind of incompetent fool would do such a thing. But then again, there's a good thing there's no mirrors in this room right now. So if you accidentally do that, you'll notice, you'll stop and think, wait a second, 36 is close to 30 and the sine of 30 is a half. So I don't think it should be that far above half. Half of 150 is 75. So if it was a 30-degree angle, then the altitude would be 75 feet. It shouldn't be all the way up to 120. Something has gone wrong. One of the other analogies that I like to think of is that a good friend of mine, the DM, well, he's a DM on one day and he's a player in my game on the other day. He's an accountant and he is way better at arithmetic than I am. I know more math than he does, but he's much better at the math that most people interact with. He's better at arithmetic. And better at arithmetic does not just mean being able to calculate things fast. He can calculate things fast because of his experience and his training as an accountant. He can calculate things really fast, but that's not what makes him good at arithmetic. What makes him good at arithmetic is knowing that he just multiplied 150 by something that's a little more than a half. It shouldn't be 121. That's being good at arithmetic. Looking at a spreadsheet and saying there's something wrong with this answer. Just knowing that there's something wrong with this answer because these numbers don't look right. That's not what this answer should be. The experience, that's what's being good at arithmetic is about. So that you don't just blindly plug things into your calculating machine and type them as the answer on a quiz and thus confuse a bunch of students in your class. Just for example. You know what I mean? So yeah, it gives us a good baseline for these values. We're reinforcing the notion that sine of theta and cosine of theta are always going to be between -1 and 1. And so when we start graphing sine and cosine and start looking like this, it makes a lot of sense because we know these values. And we're constrained by this unit circle. So the x's are always between 1 and -1 because the x is just going to go back and forth like this. And the y's are just going to go back and forth between 1 and -1. So when we start stretching out the unit circle onto a number line, the picture matches our intuition that we've been building. Make sense? All right. Oh, yeah, you were all blurry, so now you're not all blurry. All right, so that's going to do it for today. I will see you all on Thursday. Learn your values, draw a bunch of unit circles. Just have to go from 0 to 360 for 30, 45, and 60 and the quadrant angles. Start working on that. Start learning those values. That's going to do it for today. I'll see y'all on Thursday. Everybody have a good couple days, and thanks for playing.